Buenas tardes y bienvenidos a las conferencias de la Fundación Ramón Areces. Good afternoon, Professor Ferdi Schüth. Good afternoon, Ferdi. Extremely happy to have you here. And I'm going to do your presentation in Spanish because I want to puntualize each one of the things that I will say. El profesor Schüth estudió Química y Derecho, interesante, ambas dos carreras, recibiendo su doctorado en Química en 1988. Realizó sus estudios postdoctorales en la Universidad de Minnesota en 1989 bajo la dirección del profesor Lynn Smith. En el 93 fue profesor visitante de la Universidad de California en Santa Bárbara y desde el 95 al 98 fue profesor de Química Inorgánica en la Johann Wolfgang Goethe Universität de Frankfurt. Desde 1989 es director del Max Planck Institut für Kohlenforschung en Mülheim. Y desde el 14 hasta junio del 20 ha sido vicepresidente del Max Planck Gesellschaft en Múnich. El profesor Schüth ha recibido numerosos premios nacionales e internacionales a su labor investigadora y es doctor honoris causa por la Universidad de Tecnología de Dalian y la Universidad de Tecnología la TUM de Múnich. Fue fundador de la compañía HTE, siendo BASF el principal accionista. Esta es una compañía con gran éxito y con la que nosotros tenemos colaboración directa. El profesor Schüth trabaja en energía, conversión de biomasa, síntesis de materiales para catálisis y almacenamiento de hidrógeno. Y de sus investigaciones ha publicado alrededor de 500 trabajos de los cuales muchos son altamente citados, y es coautor de más de 40 patentes. Combina con gran éxito la visión del investigador en su laboratorio y la gestión y planificación de la investigación en Alemania. Este es el punto clave por el cual nosotros le pedimos que estuviera hoy con nosotros y que dividiera su conferencia en dos partes. Una primera parte en la que nos hablara de cómo se organiza el sistema de investigación estable y vertebrado que existe en Alemania. Queríamos que nos dijese cuáles son los principales actores y de qué manera actúan en el proceso de generación de líneas de investigación y de financiación. En una segunda parte queríamos, y así lo hará, que nos diera su visión sobre las líneas de investigación prioritarias en estos momentos en Alemania, teniendo en cuenta que hoy en día la investigación va más allá de conceptos nacionales y tiene un carácter mucho más global. El profesor Schüth, como podrán apreciar, es un excelente y clarividente conferenciante. Es habitual en muchísimas conferencias plenarias, en distintos campos de la investigación, además, en materiales, en energía. Sus conferencias siempre son altamente atendidas. Otra de las características, desde mi punto de vista remarcable, es que tiene una visión amplia de los problemas científicos y técnicos, y eso espero que lo podrán apreciar hoy también. Professor Schüth, Ferdi, thanks very much for accepting the invitation of the Fundación Ramón Areces. For me, it is a double pleasure. First, to see you, even if it is online. And secondly, because I always enjoy and learn from your talks. Now, the floor is yours.
Ladies and gentlemen, it's a great pleasure for me to speak here for the Fundación Areces about future research directions in Germany. When I discussed the content of the presentation with Avelino Kormar a few months ago, I told him that it would certainly be a limited view on future research directions because I was responsible for a small part of the research system in Germany for the chemistry, physics, technology section of the Max Planck Society when I was vice president and have relatively deep insight into these fields, but of course I have also seen and heard about other fields, and so I try to give a somewhat balanced view, but keep in mind it will be biased towards chemistry, physics, technology, because that was the kind of problems I was most exposed to. The second disclaimer I would like to make is the fact that I will not cover big international infrastructural projects, as exciting as they may scientifically be. Let me just give you an example of what I will not cover. We have about 5 years ago detected gravitational waves for the first time. Momentous discovery, great discovery, and this field is now both looking further into the detection and analysis of gravitational waves, but it's also becoming or will become a tool for astronomers to do gravitational wave astronomy. For that you need either big space missions to put interferometers in space, or you need multi-billion euro infrastructures like the Einstein telescope, which is on the planning horizon in Europe. This is way beyond what can be done on an institutional or even on a national scale, and so this has different types of discussion forum where such things are discussed. So I'll be a bit more restrictive. What I also want to do is to start out with a brief description of the research organization in Germany, because that is also an important question. How do new topics appear on the horizon? How are they developed? Who develops them? And that has to do with the research organization in Germany. From the distance in Germany, we have something like 6 types of players who are carrying out research. There are smaller ones who also do research, at least in the public domain. Industry is not on this slide, but these are the bigger ones. I'm from the Max Planck Society. Mission of the Max Planck Society is basic research, curiosity-driven, open to applications, but the driver is scientific curiosity. Budget on the order of 1.7 billion euros per year. The counterpart in the system is the Fraunhofer Gesellschaft. They are more working on application oriented research. Very often in collaboration with companies, it's very often targeted really at products. They are also organized in institutes, often cooperation with also the local industries, but also national and global. So roughly the same size as the Max Planck Society. Rightfully in the center of the slide are the universities. The universities are the basis of the research system. There is great research being done in universities, but the universities are also responsible for educating our young scientists. And so if we don't have the universities, a system is essentially hollow. So that's the centerpiece of our science system. Below the universities are what is called here the Applied Institutes of Higher Education. In other countries they are called polytechnics, for instance. In Germany they often now call themselves Universities of Applied Sciences. They are more application oriented. The education there is more targeted on the needs of industrial companies, less so for the needs of high science. Typically not PhD granting institutions, and the regular degree is a bachelor's degree. Most people at the Applied Institutes of Higher Education in Germany, they are called Fachhochschulen, they leave their institution with a bachelor's degree. And as I said, mostly not PhD granting, but there is some research being done also at the polytechnics. Here in the corner we have the Helmholtz Association. The Helmholtz Association is a union of the almost old nuclear research centers, big research facilities, which were converted to work on the big societal challenges. I'll talk about the challenges which are worked upon later. They also operate the big infrastructures in Germany. So synchrotron facilities, for instance, are operated by the Helmholtz Association. And then we have the Leibniz Gemeinschaft, a very mixed bag, I would say, of research performing institutions. There are research museums amongst them, the Deutsche Museum, the biggest technical museum in Germany, in Munich, great place. If you have a chance to visit, I would recommend you to do it. Is a member of the Leibniz Association, but also really high profile, high level research institute. The LICAT for catalysis in Rostock is such a system. The Institute of Solid State Research in Dresden, more than 1,000 people working on solid state problems, is one of the Leibniz Gemeinschaft. So this is a very mixed bag. So clear mission, Max Planck basic research, Fraunhofer application-oriented research, Helmholtz program research and infrastructures, and then as the centerpiece for the research system, the universities. We have two or three other important elements. These are research performing organizations. These are the funding organizations. German Science Foundation, German Research Foundation, DFG, gives money for fundamental research, curiosity-driven research. Whenever you have a great idea which is scientifically convincing, original, excellent, the German Research Foundation, DFG, will most probably fund your project. Then there is the ministries. This is the Ministry for Research and Education, Education and Research, but it's pass pro toto for all the ministries. Most ministries fund to some extent also research activities. They have typically program activities. They identify needs for Germany, and then they have a call for proposals, and then you can submit. And finally, the whole system in Germany is funded partly by the states of Germany, who are directly responsible for the universities, partly by the federal government. And the Gemeinsame Wissenschaftskonferenz is a body where the states and the federal government come together and decide upon the general directions, the rules according to which research is funded, and so on and so on. That gives you an overview over the landscape in Germany. All of you know, if you do research, it's expensive and you may need funds for that. There is institutional funding. It depends highly on the organization you are in. In most universities, if you are a professor, your salary is paid by your organizations, the facilities are paid by the organization. You may have funds for 0 to a few co-workers who are also used for teaching activities. You may have some 10 kilo euros, depending on the field, for consumable small expenses. That's at the universities, and it depends on the type of university you're in. If you're at a low-level university, your funds will typically be smaller than you are if you are at one of the most prestigious universities and you have gotten an offer as a very established scientist. So then, in order to attract you, your package will be somewhat bigger. And it goes to very, very substantial funds for the Helmholtz centers or for a Max Planck department. So a Max Planck department, the whole department overall, including everything which you need to run a department, is on the order of a few million euros. Depends on the field, but that's approximately the size. So that's institutional funding. Then we have the DFG, German Research Foundation, scientifically extremely important in the German system. You need to be active in the DFG to be an acknowledged researcher, and the standard program is the single grant. You have an idea, you write it up, hopefully it's convincing, you send it to the DFG, it's decided upon by your peers, and then eventually you'll get a funding decision or not. Financially, it's typically normal program, rather small. You may get one co-worker PhD student, postdoc, you may get a few 10 kilo euros for consumables. The typical duration is 3 years. Sometimes you may be able to ask for equipment. And there are coordinated programs where many groups come together, a whole department or something, a fraction of a department in a university, and then the funds are substantially bigger. The money provides a very high degree of freedom. As I said, any idea is eligible. No program, if you have a great idea, no matter from what field of science it is from, there is a chance you get funding. Similar to the ERC, which you know extremely well, it's highly competitive. It often has an award-like character. It's typically way more money than for a normal DFG project, and the money is very flexible. So that's, to some extent, that's the flagship program in third-party funding, and everyone wants an ERC fund. About 15, 20 years ago, the Excellence Initiative was created in Germany, which was supposed to, first of all, bring more money into the system, but also in order to fund in a very substantial manner excellent parts of the research system and excellent universities. And there are two funding lines. There are excellent clusters, topical projects on a certain field of science, where you will be awarded 3 to 10 million euros a year, and the universities can run for excellence status, for infrastructure, for specific strategic programs, gives the university 12 to 15 million euros a year, also very substantial money where you can do something. Ministry funding, interesting. It's typically networks, industry and academia, because this is often translational research targeted at something which should be eventually implemented in practice, typically upon a call. You cannot just, as in DFG, always send in applications. There is a call, you have to answer the call. The topic of your project has to meet the topic of the call. The agenda is set by the ministries. The ministries, in discussion with scientists, try to identify where do we have research needs. Well, and then there is a call. Financially, these are often very attractive, but there is tight controlling of timelines, deliverables, and so on. You all know the EU projects, networks, high international collaboration, administrative cost, both financially but also organizationally, rather high because you need to manage these networks, but they are financially not unattractive and so quite interesting. Industry funding is important depending on the field, of course targeted at the interests of the industry. They want to achieve some very specific goals. The money is typically flexible because as long as you deliver on the project promises, the companies don't care so much how you exactly spend the money, as long as the performance is okay. And then there is a whole range of different ways to attract additional money. Stipends from the, let's say, Humboldt Foundation for people coming from abroad to Germany or sent from Germany abroad. Big foundations, the VW Stiftung is a very generally funding organization with substantial resources, and many, many others. What I have described so far is the regular project funding. What is difficult to fund is really long-term, high-risk projects. You can do that from institutional funding down here. Max Planck is set up in a way to allow this kind of long-term, high-risk projects from institutional funding. But if you're in a university, you have to come up with other means. And you can have industrial funds which you deflect. As I said, as long as you perform in your industrial project, industry doesn't care how exactly the money is used, and that's something you could do. We have two types of big projects from the DFG. The Reinhard Koselleck grant is something like the ERC grant, about the same size, rather similar, also very lean, very general description of what you want to do. and thus very flexible funds. And there is the Leibniz Award, which 10 high-level scientists from all fields of science receive per year in Germany. It's 2.5 million euros for 7 years. So that's a pretty generous funding, no strings attached. I talked about ERC, which you know. In networks, such as the priority programs, like Excellence Initiative, there is typically flexible money available, which you can use for long-term research. I already alluded to institutional funding. And finally, the ministries are not supposed to fund infrastructure. They are only allowed to do project funding, which was limited to 5 years until a few years ago. And then a new instrument was introduced for the example of the so-called Copernicus projects. They are for 5 years, but there is the promise, if this works out, it'll continue, and it's a bigger and longer term initiative, so that it is not just the 5 years, it's the 5 years plus a lot more. Although you have to renew your project after 5 years, but that allows you to do it. On the societal level, just a few remarks on the numbers. The goal in Europe is to have 3% of our gross domestic product for R&D. In Germany, we currently, 2019, have 3.2%, which is on the order of 110 billion euros. Breakdown approximately 1/3 from the public sector, state and federal government, 2/3 from the private sector. Here are the numbers till 2012. Here is more recent numbers in form of a graphics up to 2019 with numbers from this year. And here you see essentially the same breakdown. Let's take 2019, roughly 2/3 from the private sector, R&D expenditure of companies, 1/3 from the public sector, federal and state money, a little from non-profit organizations like the VW Stiftung. It looks like a little, but this is billions. So this is 400 million euros. So this is not really a little. And then 8 billion euros from abroad, which is mostly European money. Now we are slowly moving to what is high on Germany's research agenda. And the first question is, who sets the research agenda? I have to say these are typically not pure examples. There is always many influences on research agendas, but this is more or less a general idea who defines a research agenda. In the Max Planck Society, it's easy. It's the scientists. Each director decides in the department what the direction of the department should be. And on the level of the society, directors come up with ideas for new departments, for new institutes. They are discussed with the leadership of the society. They are discussed with the colleagues in the section. And at the end, there is a vote of the section. All the scientists in the Max Planck, the scientific directors of the Max Planck Society, whether to move forward with an initiative. So that's really a bottom-up driven approach, how new directions are identified. The same holds for the DFG, German Research Foundation. There is no programs in the DFG, no topical programs. Nobody in the DFG says, now let's have a big initiative on gravitational wave astronomy. It's scientists who come up with great ideas. They submit their proposals to the DFG, and then it's decided upon either positively or negatively. But it doesn't need to be according to specific topical lines. Any field, any initiative is eligible. That's somewhat different for the Helmholtz Association. The Helmholtz Association has a high-level political agenda working along big societal challenges. And the fields along which the research in the Helmholtz Association is organized are listed here: energy, earth and the environment, health, aviation, space traffic, matter and information. This is the internal organization. There is influence from the political side, what should be done. This is moderated by the Senate of the Helmholtz Association, where these things are discussed in a bit more detail, and then it's detailed by the scientists doing actually the work in the centers, working on projects. But every 5 years, there is the so-called program-oriented Forschungsevaluation, where these fields are looked upon, the activities in these fields are scrutinized, and it is decided how much money is allocated in this direction, how much money allocated in this direction. It's high-level political agenda, but it is a political agenda. In the VW Stiftung, as the biggest private foundation, there is a mix of the people in the bodies of the foundation, which are also often scientists, and scientists who come up with ideas what the VW Stiftung could fund, and that holds also for other foundations. And then finally, funding from the ministries, which is a very, very substantial pot of money given to the German science and research system. There is a clear political agenda. The ministries ask, also in consultation with the scientists, ask themselves, what is important for Germany? Where should we fund research which could advance Germany as a whole? Now, having said this, who sets the research agenda? Now comes the question, what is high on the German agenda? And I want to remind you of the two disclaimers I made in the very beginning. So what I'm now telling is certainly not complete, and it's biased by my personal view. And also these elements on the agenda, from what we currently do and is being implemented, partly done, to something which is maybe more on the horizon for future activities, I'll highlight in some more detail in the following a bit less than 30 minutes or so, and try to give you a feeling what is being done in Germany and how these things are being implemented in the German research system. And I'll start with the energy transition, everything which has to do with the energy transition. You all know the world, Spain, Europe, Germany, the whole world is going through a massive transition from fossil energies to renewable energies to fight climate change, reduce CO2 emissions, and so on. And if we harvest our energy, the needs of our society for energy from renewable sources, the two most important ones are sunlight, photovoltaics essentially, maybe solar thermal plants, but mostly it's photovoltaics, and wind farms. And all of you know, if you have wind or sun, the wind is not always blowing, the sun is not always shining. Especially in Germany, maybe you in Spain too, but probably more we in Germany, there is dreary November weeks where there is fog around, not a trace of wind, and the fog blocks all the sunlight. Now, if we rely on sun and wind alone, then we certainly have a problem here. And what I've plotted here is the wind power and the solar power in about a quarter of Germany. That's the grid operator. 50 Hertz is the grid operator in essentially Eastern Germany for, this is 2018. March 2018, I think I downloaded here. You can download it with a 15-minute resolution from their homepage. And what you see is, well, the sun only shines during the day. At nighttime there is nothing. And the wind energy changes between essentially 0 and something like 12, 14 gigawatts of power. The average power consumption of Germany is 65 gigawatts. So this change is roughly a quarter of Germany's power demand. And the grid has to cope with this type of fluctuations. And there is many ways of doing that. You can extend the grid, you can have backup capacity, you can do demand-side management. But one important way is storage on different size and length scale. And here is plotted the typical size scale of storage and the typical time scale of storage. On the level of a nationwide electricity grid, on the level of a society, we are talking about this range here. Long time scales, very big amounts of energy to cope with, let's say, 2 weeks of fog and no sunshine in November. And this need for storage is the reason why Germany has announced about 1.5 years ago the hydrogen plan. Because from electricity you can get to hydrogen by electrolysis, and that's a relatively straightforward thing of creating hydrogen from electricity, and hydrogen you can then store in subterranean caverns, or by other means there is large-scale storage of hydrogen possible. And then you have to ask yourself, what do we need to do with the hydrogen? What type of research activities need we in order to implement a hydrogen, or at least partly hydrogen-based society? So we have electricity. Electricity will be converted to hydrogen, and the electricity can be generated in Germany, in Spain, or in Australia. If we convert it into hydrogen, we can then transport the hydrogen to the demand centers. And one should think about hierarchies of hydrogen use. My hierarchy is first replace fossil hydrogen, which has a high CO2 footprint in the chemical industry. Avoid CO2 emissions in other industries. The steel industry emits a lot of CO2. If we could make steel with hydrogen instead of with coke, then we could save very substantial emissions. We can use the hydrogen in fuel cell cars. We can convert it to liquid energy storage compounds. Easiest, make hydrocarbons, make diesel fuel from hydrogen and CO2 captured from the air. And the final one is reconversion to electricity, because the cycle overall has so many losses. I would not do that easily, but rather use these other uses. And we need research activities to implement them on the society level for all of these different elements. Just as one example, hydrogen for the steel or metallurgical industry. Here is the numbers. We have 70 million tons of carbon dioxide in the steel industry in Germany. Very, very emitted, very, very substantial. And that the reason is that we use coke, essentially C, to reduce the iron oxide to metallic iron. If we would do that with hydrogen, and the hydrogen is generated from renewable electricity, we could essentially save these 70 million tons of carbon dioxide. And there are pilot projects running where one tries to do a reduction instead of in the big blast furnaces, in other units where you essentially create an iron sponge by reducing the iron ore with hydrogen. Many questions around it. What about the hydrogen content in the final steel? What about materials problems? How can we run the process that it goes to completion and we really have pure iron and so on? So that's a very interesting one, and the CO2 footprint could even be reduced if we create the hydrogen from natural gas by steam reforming, because that would overall leave a lower CO2 footprint. If we convert the whole steel industry in Germany to hydrogen technology, we're talking about 20% of Germany's current electricity consumption. Very big chunk, something very important. And steel is not the only metal which we are producing in a highly CO2 emitting fashion. So hydrogen metallurgy is something which should be very high on our research agenda. Storage in compounds, ideally to keep all the infrastructure in place, and I come to that later, could be a really attractive pathway. And we need examples how to do that. Water electrolysis creates our hydrogen. Thermodynamically, that costs us 33 kilowatt hours per kilogram of hydrogen. Practically, it costs more, let's say 50 kilowatt hours per kilogram of hydrogen. Steam reforming hydrogen comes at a price of €1 per kilogram. Depends on the natural gas price and so on, but let's take this number just as a global one. Which means if the electricity is more than 2 or 3 euro cents per kilowatt hour, this will never be competitive unless the CO2 costs for the current methane hydrogen production route would be very high. But in your area of Europe, in Spain, Portugal, actually prices for photovoltaic electricity may come down to these levels. I saw that the lowest bid for the kilowatt hour of electricity generated for a power plant was $1.3, so even less than a euro cents, one in Portugal last September. And if we talk about these costs for hydrogen, then it could be interesting to produce chemicals in Southern Europe, in Spain, in Portugal, in North Africa, in the Middle East, and then transport them to Germany. And if we make Fischer-Tropsch hydrocarbons, well, we could even use our existing infrastructure. This needs to be tested, this needs to be done on technical scale, it needs to be economically analyzed, but generally it seems to be possible, and that could give us a CO2 neutral hydrocarbon if at the very end we capture the CO2 from the air. So we would capture CO2 from the air. This is an artist's impression. This is not a real world plant, just to make that clear. If we capture CO2 from the air, if we make hydrogen from renewable electricity, if we combine the two chemically to produce, for instance, a hydrocarbon or methanol, we can ship it, we can combust it even at the destination and be overall CO2 neutral because the carbon has been filtered from the air to get going at the beginning. So this is something which overall one could keep in mind if one thinks about a hydrogen energy systems. This is just the technology you would use. You essentially use a chemical looping to produce limestone and filter it like this. Moving for a while away from energy to another currently very pressing research topic, which essentially has been put on the agenda due to the corona pandemic. I mean, Spain was hard hit, the whole world was hard hit, and that made us aware of a number of things which are really, really important and which we had overlooked. The first very important research question resulting from the corona pandemic is, what lessons should we take from this pandemic? What lessons should we learn? How should we adapt our system to cope better with a future potential new pandemic? And so we need research, and this is being done in Germany. There are programs underway. We need research into the adaptation of the public health system. Just the lack of information, the slowness of response was initially a big problem in the pandemic. It would be really, really interesting, but scientifically extremely challenging to look into the mitigation coping intervention strategies which have been implemented in different parts of the world. The UK, Spain, Indonesia, China, the US, Germany, they all have reacted differently to the pandemic. And it's up to now not totally clear what the best strategy under which circumstances is. If we would look deeply into this whole set of intervention strategies and their effects, we could actually hopefully learn for a new pandemic what to do with it. It would also be interesting, and that's for society as a whole important anyway, to make our societies more resilient, which means less sensitive to external influences, more adaptive. Let's take the example of the logistics chains, which were interrupted during the pandemic. How should we adapt our societies? What is a good model for societies, for the economy and so on, to make them less sensitive to such interruptions from the outside? Create resilient systems. And I think it would be important, although we were extremely quick as science, but also as societies, to develop vaccines for the coronavirus. We need fast response development of assays to analyze an infection. We need fast response drug development. We still have not a drug. We have a vaccine, which is wonderful, but when you are terribly sick from COVID and you are in the hospital, intervention strategies, treatment strategies are very limited, and so it would be great to have drug development speeded up, and we have to put structures in place, do research into development of such interventions in order to be quicker, hopefully, in the next potential pandemic. With respect to structures, the science system in Germany has actually responded in a great manner, very fast to the corona crisis. And this was, I think, partly due to the fact that we had both structures in place, the Robert Koch Institute, our National Health Service Infection Institute. There is a Helmholtz Center, the Helmholtz Center for Infection Biology. There are many Max Planck Institutes where there is essentially scientists with the freedom and the leeway and the resources to change their research direction from one day to the other. And we had many scientists who saw the challenge, who saw the problems we had, and who basically changed their research activity in a matter of a week and did corona-related research. And I think this was one of the ways how Germany could cope with it. If we take the lesson a bit further, what goes beyond the corona pandemic, and which is also high now on the German research agenda, the coronavirus has spread from animals to humans. This is the so-called zoonotic diseases, germs which are endemic in an animal and for some reason make the transfer to infect humans. We have to find ways how we avoid the spread of zoonotic diseases. That may be medical interventions, that may be scientific interventions, that may be political interventions. Ban trade with animals, with live animals especially. And so that's a challenge. One thing which was extremely successful in the corona crisis was the development of the mRNA vaccines. Both the BioNTech and the Moderna vaccines are based on messenger RNA. These companies, I know of BioNTech, they have worked on mRNA for over 20 years to fight cancer, which may still be an option, to fight other diseases, or to develop vaccines. And looking more into the power of mRNA for many different medical purposes is certainly something which has moved much higher on the agenda by the corona pandemics. And then we have a broader global problem which we also need to tackle. We have multi-resistant pathogens where antibiotics fail, where people die in hospitals because they catch an antibiotic, catch a strain, a pathogen strain for which none of the known antibiotics works. Since often the numbers of people infected are relatively small, the incentive for the big companies to develop something against the multi-resistant pathogens is not so high than for other targets. So public funding to develop strategies to cope with multi-resistant pathogens is also a very important thing to be done in the future. Third topic, future mobility, relates back to the energy question, but in a very specific manner. We will have much more electrification. This is from a paper from 2012, but the development trajectory is still the same. We are currently in the field of lithium-ion batteries. We will move to other battery technologies which have a higher energy storage density, And this type of battery technology, electromobility basis technology needs to be developed. Also very high on Germany's research agenda, but it's not only the chemistry and the single cell development. Equally important for industrial production is to know how you do that on the scale of 1 million cars per year. And how do you recycle the batteries, because we cannot just dump them after their end of life. We have to recycle the materials from the batteries. And so, for instance, we have a big research fab battery cell in Germany, in Münster, which really has the task of developing industrial scale solutions for the production and recycling of battery cells. So that is something very important. We shouldn't forget, though, not everything will work with batteries. Although the A380 production is discontinued, planes of that size will not fly on batteries. There is no way. The same probably holds for heavy-duty trucks or ships. And so we need different solutions for other types of heavy-duty traffic. How could we guarantee a CO2 neutral mobility? And we need research into that. And I go a few slides back. If we produce with solar electricity, hydrogen, and CO2 captured from the air, kerosene, diesel fuel, well, then we can, in a CO2 neutral manner, fly planes, run ships, run big trucks. And overall, maybe we should change our whole mobility system. More public transport with different means. Seamless integration of trains, cars at the destination, use the cars instead of own them, so new models, how you deal with mobility, fully autonomous vehicles. So also a very interesting development there. And with the fully autonomous vehicles, I come to one of the very interesting and broad fields in the scientist system, artificial intelligence. It's almost a buzzword. It pervades essentially any field of science and technology now. In most projects, or in many projects, research proposals I see, there is an AI element in there. It's pretty clear that one needs to embed AI specialists in the domain of research, but it also requires generic artificial intelligence research. We need new algorithms, new concepts, many approaches for different fields to implement artificial intelligence. A very specific problem is that the competition between the academic and the private sector is extremely fierce. The private sector pays higher, much higher. I know some of the salaries there, but it provides a really competitive working environment. The scientific challenges are sometimes as exciting as in the science system. And so for universities, research organizations to compete in hiring with the Googles, Microsofts, Facebooks, Amazons of this world can be a challenge. I want to give you one example how we have tried to meet this challenge in Germany. It's the Cyber Valley, which we created in the southwest of Germany with two key people, very high-profile AI researcher Bernhard Schölkopf and Michael Black from the MPI for Intelligent Systems. You need to create critical mass, and what they always said is you need to create to attract the cool kids on the block. People want to work in a cool environment in this field, not just in a challenging environment. And so we tried to create an innovation infrastructure where universities, Max Planck Institut, industrial companies joined hands to have a whole chain of different elements, startups, technology transfer activities, specific research groups, specific professorships, teaching graduate students and so on in many different structures. And over something like 3 years, and I, for the Max Planck Society, was primarily responsible for this, from 16, where we basically signed the original document to create Cyber Valley, to nowadays where this is an implemented, highly visible structure, we were able to attract a number of different partners to Cyber Valley. Something which we are pretty proud of is that we could get Amazon to create a research center in Tübingen as part of the Cyber Valley activity. That took a lot of initiative, a lot of work from Bernhard Schöllkopf, Michael Black, the state of Baden-Württemberg, funding, promise of buildings, discussion with the partners to find something. But at the end, everyone was convinced this is the right way to go. If we want artificial intelligence, we have to bring many people together. It cannot be an isolated activity. You need critical mass, and that's what we have created in Tübingen, Stuttgart. Very much related, a much more amorphous research field currently, the field of social computing. Social computing is the intersection between social science and computer science, and there are many interesting research questions which need to be formulated and solved in social computing. It requires really a close interaction because the computer scientists who know about the technology and social scientists. And I'll give you some of the examples of the research questions. Can artificial intelligence algorithms, which decide upon whether you get a loan or something else, can they be discriminating although they are constructed in a totally unbiased manner? To answer this question, yes, they can. If you don't implement it in the right way, they may discriminate against women, they may discriminate against certain ethnicity, they may discriminate against certain neighborhoods. And this is a very subtle question which needs to be studied in detail, since these algorithms make important decisions nowadays. What all of us know, at least those of us who have kids, but basically anyone, how do social networks influence social behavior? If we don't meet people personally anymore, but I'm connected to everyone by WhatsApp, Facebook, whatever. Currently, how do video conferencing tools affect our interactions? What do we lose? And this is not totally clear. How does technology influence the spreading of fake news, something we have seen in the US, or the creation of filter bubbles where people only realize one part of reality anymore? So that's also a big question. Also related, cybersecurity, one of the very big threats. Our societies are vulnerable, highly interdisciplinary field. High on the agenda in Germany, we have 2 centers created, the CISPA in Saarbrücken, it's a Helmholtz Center, and the MPI for Security and Privacy in Bochum. That requires expertise from cryptography, computer science, psychology, law, social sciences, because it's not just a technological problem. What does the best password technology help you if people write their password down and tape it to the screen of their computer? So that's then the domain of the social scientists. And the Max Planck Institut, which we have created 2 years ago in Bochum, exactly does that. It integrates computer science, social sciences. Quantum technology may lead to another quantum leap. There are different elements to quantum technology. This is from the Quantum Valley, the Munich Quantum Valley, where Max Planck plays a major role, strategy paper. Quantum cryptography communication overlaps with the cybersecurity problems. If we can solve the factorization problem, which quantum computing promises to do, then our encryptation algorithms are not safe anymore. Germany has decided to fund quantum technologies with overall 2 billion euros for the next 5 years, especially for the design and construction of a quantum computer. It's totally unclear which type of quantum computer will at the end be the one who wins out, who is the best technology. There are atoms, ions, manipulated ions, superconducting circuits. That's the currently running ones. Germany has in the southwest bought the first IBM system, the first quantum computer in Munich. Here is a photograph. There could be spin-based system, photon-based system. This is closest to realization. You can actually get them. These are also a bit nearer. These are further out in the future. We need to work with them to see what you can do with them. But it doesn't stop. Oh, wrong direction. It doesn't stop there. Beyond the computer, we need the application cases to be developed. We need people to work with them to see what you can do. We need quantum information theory. It's currently not totally clear how reliable the results are. How do you verify the results of a quantum computation? We need software development for quantum computing, very strongly interlinked to the hardware development. It needs to be embedded in an environment. It's not an isolated unit. We need hybrid systems where a quantum computer is interfaced with regular computers, and there is also activities in simulating quantum computers on conventional systems to learn more about them. Very big, extremely interesting, important research field. Coming to 3 last slides on things which are further out on the horizon. Biodiversity is an extremely important research topic. You may know that we are losing species at a very high rate. Especially this holds for insects. That is affecting pollination. Our plants cannot be pollinated anymore if we don't have bees and other insects anymore, which would lead to a crisis in agriculture. The knowledge about the loss in biodiversity is sketchy. The knowledge about the ecosystem function of many species is sketchy, which means intervention strategies are very difficult to orchestrate. What do you do about the loss of biodiversity? We have recently launched a Max Planck Center on insect ecology between Sweden and the Max Planck Institut in Jena. There are thoughts of a real-world ecology laboratory, a big piece of land which you basically leave unaffected and where you try to study intervention strategies. It means really a big piece of land, not just a few hundred square meters. And that could be an interesting research agenda. From my field, chemistry, I think one of the most exciting questions is that of the construction of life. I would say chemistry of the molecule and chemistry of solids has reached a relative high level of maturity. We can do a lot. But the chemistry of interacting entities, interacting molecules, is little understood. But that's exactly what happens in life. Many, many chemical species interacting with each other and creating what we call life. The origins of life on Earth are difficult to study because the traces have gone through so many changes. It may remain a metaphysical question. Maybe yes, maybe not. But a big research question is, can we construct the elements which constitute lifelike systems? Either from the elements which we found in life today or from any set of any compound. It doesn't need to be a carbon-based life if it has the elements. And it needs compartments. It needs active exchange of matter between compartments. We need to construct autocatalytic cycles. We need to develop methods for information transfer. We need energy transformation elements in a system and a theory to describe how molecules and assemblies interact to create something like life. And even if we don't succeed in constructing life, we will develop a lot of new chemistry if we embark on such a program. And the final one, maybe one of the biggest, almost philosophical questions, the science of the Anthropocene. Paul Crutzen, Nobel Prize winner from the Max Planck in Mainz, has coined this term. The Anthropocene is a Earth geological term describing that mankind now is a geological force. We are changing our planet because we are here and we work with it. We lead to global warming. And this is a many-faceted scientific topic. We need global change analysis, natural science, international law. Is one country allowed to use the atmosphere, which belongs to the whole globe, to dump CO2 in it? And what is the mechanisms to govern this? We need sociology, philosophy and ethics of the behavior of the interaction of people using common goods. Extremely complex, interesting questions which also need to be on our research agenda. With this run through, I put the list up again of the different topics I have touched. As I said, with the disclaimer, it's a personal biased view, but I think these are all really, really interesting current and future research questions. Many thanks.
Thanks very much, Professor Schüth, for your excellent lecture. And I am sure that the rest of the audience have enjoyed as much as I did. Now, what I am hoping is that soon we'll be able to travel, and soon we'll have you in person here in Spain, and we'll remember good old days as well as we'll discuss about science. Thanks again, and all the best for you and yours.